Welcome to a quick screencast in which I review the computer laboratory session on linear regression. In that session, we were using the inverse square law Excel spreadsheet. That spreadsheet contained some radiation data that had been measured different distances away from a radiation source. We know that such a system could be modeled theoretically with an inverse square law relationship that takes into account a background radiation term. And such an expression is given here. Counts are our measurements, and they are being modeled with this model expression here. That expression has two terms. In each term has a parameter, A1 and A2. The A1 parameter is associated with the 1 over r squared independent variable. The A2 is associated with the constant background radiation term. And because it's a constant term, then it is associated with an independent variable that is set to 1. More generally, linear equations like this can be represented by this equation here, where y represents the set of measurements, the dependent variables. X represents our basis functions that we use to construct our model expression, our independent variables, and associated with each of those independent variables are our parameters. And in this expression, we have m parameters. Right, so we need to first calculate the independent variables. So in cell G2, I will calculate 1 over r squared. So equals 1 divided by E2 squared. Can also complete that quickly, like so. The background radiation parameter has independent variables set to unity, like so. Now that I have my independent variables, I can go to the data analysis toolkit. To do that, I need to click the Data tab and then click Data Analysis, highlight Regression, click OK, and then in the pop-out window, I have to input the measurement cell range, the independent variable cell range, and I also want to check the labels checkbox and the constant is 0 checkbox. The constant is 0 is being checked because I am forcing the system to calculate a constant term. I don't want Excel to do it for me. So in the input Y range, because I've checked labels, I can include the F1 header label. So there I just highlight the cells F1 through to F11. For the X range, I need to highlight G1 through to H11. Okay, so I've highlighted both columns G and H associated with the independent variables. When I then click OK, a new worksheet appears that contains all of the regression data that comes out of this model fitting. Right, now let me just expand the A column because I can't read everything, and the easiest way to do that is to take the cursor to the region between the A and B columns until I get a double headed arrow cursor and double click, and that will now increase the cell width until I can read everything. I can do the same with column B and column C. This gives me a great deal of useful information. Notice here it's telling me I have 10 observations. Notice it's also telling me that there are 2 degrees of freedom associated with the fitted parameters, 10 degrees of freedom in total. But once I've fitted the data using 2 parameters, I only have 8 degrees of freedom remaining. The final table down here tells me the values of the parameters associated with the 1 over r squared independent variable and the background constant independent variable. And indeed, in column C, I also have the errors associated with each of these two parameters. I just want to highlight the parameters and the standard errors in those parameters and take a copy of them and move them into the original worksheet. And I will paste them into cell B2. I'm going to paste them as special as values so I don't bring over any of the formatting. Okay, I've done that there. Great, so there we go, linear regression in a nutshell. One of the problems though is that the linear regression that you do using the data analysis toolkit assumes that the uncertainties, the measurement errors associated with each measurement are all the same. We know that for this set of data, that's not true. In fact, we know that the error associated with each radiation measurement is in fact the square root of the number of counts. We're going to perform a regression analysis that takes into account such differing measurement errors. The first attempt will be done using Solver. So if we move now to the inverse square law solver worksheet, it will look something like this. So first of all, let's calculate the errors associated with each of those radiation measurements. And as I've just explained, that's equal to the square root of the number of counts. Excel has an inbuilt square root function, which is sqrt. Great. I also need to recalculate the independent variable, so that's going to be 1 over d2 squared. And also the independent variable associated with the background radiation term, which is just a set of 1s. And Solver is going to determine what the parameters are by minimizing the goodness of fit parameter. In order to calculate the goodness of fit parameter chi-squared, I need to calculate the model value for each of those measurements. In order to calculate the model value, I need to have an initial guess for the parameters. I'll put those initial guesses in the B column here. So let's assume that the parameter associated with the 1 over r squared term is equal to 100. It has to be a positive value because we know that the radiation counts are decreasing. And we can set the parameter associated with the constant background term to 0. Right, I can now input the model term. So let's input its formula. It's going to be equal to the parameter associated with 1 over r squared. And when I also complete this model expression for each of the measurements, I don't want the B2 term to change as I go down the column. So to do that, I need to protect B2. And one does that by putting a dollar symbol between, well, before the B and before the 2. There is also a shortcut for this, which is F4. I need to multiply that by the 1 over r squared term, which is G2. And then I need to add the second parameter like so, protect it again in the following way, and multiply that by the independent variable associated with it, which is H2. It gives me an expression like this, and I can auto-complete. And notice now that the B2 and B3 terms do not change, whereas the independent variables are changing for each of the measurements. Now that I have the model value, I can calculate the residual between them. Well, I can calculate this term here in order to construct chi-squared. Let's do that over here. So this will be equal to the measurement, let's open bracket, measurement minus model expression divided by the error raised to the power 2. Okay, so that takes into account that term. If I calculate that for each of the 10 measurements, those are the values that I get. Chi-squared will now be the sum of all of those, and there is indeed an inbuilt summation function in Excel, which is just sum. So sum, open bracket, and then I'll just highlight those 10 cells. There we go. Now that I've got that goodness of fit parameter there, chi-squared, what I want to do in order to calculate what the parameters are is I want to minimize that chi-squared expression by changing these two parameters. So this is now a minimization problem, which is what Solver does. It minimizes things, well, it optimizes things. So if I click Solver, then this pop-out window appears. The objective is to minimize chi-squared. At the moment, it's set to maximize, so I need to check the minimization cell right there. And I want to minimize that function, that chi-squared, by changing B2 and B3. So I just highlight B2 and B3 like so. Once I've done that, I just click Solve. Click OK. And notice now that this number here for chi-squared has been reduced by changing the values of the parameters to 31.008 and 148.577. Those are slightly different from the values that we calculated before because this fitting took into account the differing errors associated with each of the measurements. The problem with Solver is, unfortunately, it is not able to determine the uncertainties associated with those fitted parameters. However, we can do that because this is still a linear problem, by actually unpacking what the regression toolkit does and including the errors in the process. So we can do that using the generalized least squares spreadsheet, which is over here. Okay, so what have I included here? We are going to need to calculate a few things. First of all, let's recalculate the errors and the independent variables. So the errors were just the square roots of the counts, like so. I then need to calculate the independent variables, 1 over r squared. Like so. I'll put in my unit vector, like so. Okay. I now need to construct another vector and a design matrix. So they are given by these two expressions here. The design matrix A is simply the basis function that is being weighted by the measurement error. And the B vector are the measurements weighted by the error. So I can calculate those in the L and MN columns. So for the B vector, it's simply F2 divided by G2. And the design matrix A is going to be equal to H2 divided by the error. Now I want to auto-complete horizontally as well as vertically. And I'll be able to do that if I force Excel to not change the G component, so I'm going to put a $sign before the G, okay? And let's pull that down. If I highlight this cell again, I can auto-complete horizontally in this direction. Notice now this is I2 divided by G2. And I can auto-complete that as well. Whoops. Rid of those. Great. So these cells here are my design matrix, and this is my B vector. Okay. So to do generalized least squares, what I am doing here is essentially reformatting my linear equations that are given by this expression here using this matrix expression here. So B is simply equal to the matrix multiplication between the design matrix and my parameter vector. With a bit of manipulation, first by taking the doing a matrix multiplication of the transpose of the design matrix on the design matrix on both sides. If I then take the inverse of that expression and multiply again on both sides, you'll notice that these terms are going to lead to a unit matrix. And so we'll leave my A parameter, which is what I'm trying to determine. So my A vector then is just simply equal to this expression. So I need to use matrix algebra to calculate this expression here. And I'm going to do that in these cells over here. So let's start off by calculating the A transpose. Now to do these matrix transformations, whether it's transpose or inverse or multiplication, we need to calculate error functions. And error functions require me to highlight the cells in which the answers are going to appear. Well, the A matrix has 2 columns and 10 rows. The transpose of that will have 10 columns. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoops. 10 and 2 rows. So I've highlighted those 2 cells. And with those cells highlighted, I just write equals transpose, open bracket, highlight the cells that are going to be transposed, close bracket, and then in order to create the array function, I need to press Control Shift Enter, like so. So I've now taken the transpose. I now need to do the matrix multiplication between the A transpose matrix and the original A matrix. I'm going to do that over here. That will lead to a 2 by 2 matrix. So let me highlight 2 by 2 cells and type in matrix multiplication. And the function for that, the Excel function for that is MMULT for matrix multiplication. Open bracket. Let's highlight the A transpose cells, comma, the A matrix cells, and then Control Shift Enter. I now need to take the inverse of that 2 by 2 matrix. So again, highlight a set of 2 by 2 cells, input, and the inbuilt function for this is M inverse. Open bracket, highlight those cells, close bracket, Control Shift, return. Okay, so this matrix here is also known as the covariance matrix. and that's going to be important because the leading diagonal of that square matrix are the variances associated with each of the parameters. So if I take the square root of each of those elements of the leading diagonal, I can calculate the uncertainty of my parameters. To finish off the matrix algebra, I need to multiply this 2 by 2 matrix with the A transpose matrix, like so. So in this cell here, I will want to highlight, this is now going to turn into again, a 10 by 2 matrix, like so. I'll write matrix multiplication, open bracket, let me highlight those cells, comma, and then the A transpose cells over here, close bracket, Control Shift, return. Right. And all I need to do now is multiply that matrix with my B vector. Okay, so over here, if I do that, I should end up with a vector, a 2-element vector, like so. So I highlight those 2 cells over here, and again, it's a matrix multiplication, so M ULT, open bracket, let me highlight these cells once more, comma, my B vector, close bracket, Control Shift, return. There we go. Notice those 2 parameters there are identical to the parameters that were calculated using Solver. To calculate the uncertainty now, as I just explained, I need to take the square root of the 2 elements in the covariance matrix. So this is just going to be equal to SQRT, open bracket, and it's going to be cell 010. And for the background radiation parameter, that's going to be equal to the square root of P11. And there we go. So notice that these uncertainties are different than the uncertainties we calculated using the data analysis toolkit routine. Remember, that did not take into account the errors associated with each of the measurements, whereas this generalized least squares approach using matrix algebra does. So this is the most accurate linear regression that we performed today. That's it. I will see you again soon. Many thanks for listening.